Okay, so hi, I'm Ori. I will tell about pseudo-randomness from the perspective of mathematics. I'm going to tell you about very classical stuff. It's really the basics in our field, but I think it will be nice to see how things connect. And people always complain that everything is top level, so I hope I'm really starting from scratch. So feel free to ask questions. You can push on the button for that. So let's begin with pseudo-random graphs, which is something that goes back to probably Erdesh.
הזום מחובר? לא, כן, זה בדיוק הבעיה, אני חושבת, שאני לא יודעת אם הם מקווים להסריט את ההרצאה.
איך אני רואה? שם יש כמה נושאים לך.
למה?
עכשיו אולי אני אעשה מכיר תיקון.
זה לא מראה אותי? איך זה יכול להיות שזה רואים אותי אבל לא את זה?
רואים אותך בדיליי גם.
כן.
אבל איכשהו בלי...
אני מהר מדי. מראה הכל?
תלחץ על האדום. כן, מצלמה היא נעשה בה.
עכשיו? אבל זה היה לחוץ. בגלל זה היה לפה מעניין.
רגע, אבל עכשיו לא רואים שום דבר.
בסדר, זה יותר טוב ממה שהיה. הביזיון שהיה קודם. יכול לשים פה? נחמד.
זה חם, זה יעל, תקן בזה.
So early on, in the days of Erdesh, probably people realized that random graphs have very interesting properties, and some decades later, the idea of a pseudo-random graph arose. So I'll already start in the setting of group theory. So my graphs are going to be Cayley graphs, which means that I'm taking a 5x... זה לא זה?
זה כן צריך להיות אחד מהמיקרופונים האלה, כי זה מה שקובל למערכת של המחשב.
כאילו ללחוץ על זה? אוקיי. עכשיו? וואו. נייס. So G זה פעם... לא עובד?
לא רואים את הלוח, זה לא...
לא סוף.
אבל הקונטרול לא יכולים לנתק.
מישהו ש...
הקונטרול...
אולי אתה יכול ללבוש איזה משהו...
אולי שזה מיקרופון...
מדונה כזה.
וזה בטוח לא עובד?
לא, זה מיקרופון שקובל למצלמה.
אז אתה שומע אותי, אבל הם לא.
אני שומע אותך.
הבנתי. אז תשאלו אחר כך את... והוא יגיד מה היה.
איסאי, אתה הולך לעשות משהו?
נראה תשאל אותם.
יופי.
Okay, so G is a finite group, say size n, and S is a subset of size k, and we assume that this subset is symmetric. Every inverse of an element in the set is also in the set, and the Cayley graph of G with respect to S, let's call it X, is the graph with vertices the element of G, and edges are all the pairs of an element of G and its multiplication by an element of S. So G in G and S in S. And because this set is symmetric, it means that the graph is symmetric. If there's an edge going in the opposite direction as well. We're going to study this graph. So let's look at the adjacency matrix of this graph.
I forgot to say, people complain that the distribution of questions is not very even. Please make it even.
You mean even between the field?
Even between not me and me.
I saw that at the end of the lecture, if there's an odd number of questions, somebody has to make it even. Sure?
Remind us what the Cayley graphs are.
That's a reminder. The vertices are the element of G, and the edges are all the pairs. There's an edge from a G
But you have to
its...
turn it on. The
No, it doesn't work.
And done.
By the way.
But he means to put it on here.
Nice. Do you hear me? Wow. So there's an edge from every element of the group to all its multiplication by elements from this set. That's the definition. And it's how do you say ya'il? It's an efficient way to describe a graph. So what does the adjacency matrix does? So let's write the adjacency matrix of this graph. It's going to take a function on the vertices of the graph, which are the element of G. So let's take a real function, and after I apply to the function, it sums the values at all the neighbors. And okay, that's what it does. I could also write summing of fs minus 1g, which some people will find more familiar if you come from certain areas, but it's the same thing because my S is symmetric. So this is the adjacency matrix, and we're going to look at its spectrum. Let's call it AS because it came from my S. It's the adjacency of summing over the translation by S. The spectrum looks like that. The eigenvalues can be ordered. It's a symmetric matrix. The first eigenvalue is k. This corresponds to the eigenfunction 1. If I take a constant eigenfunction, then the it has eigenvalue k because you sum from k neighbors. So you get k after applying a, and here you have lambda 2 to lambda n values, and this is really the spectrum of the adjacency matrix restricted to the orthogonal complement of the constant functions. It's the rest. And we're going to define lambda of S, which will be the maximal one. So maximal absolute value of these eigenvalues, so not 1, 2 and above. Because 1 is the k and we know it. And this is the same thing as asking about the operator norm of AS restricted to the complement of the constant one. Because the operator norm is the maximal eigenvalue.
Even without restriction? Isn't it true even without restriction?
No, without restriction it will be k, because you have the eigenvalue k. And here's what we say: x is pseudo-random if lambda s is smaller. That's the slogan.
Slogan, but not definition.
What?
Slogan, but not the definition, right?
Slogan, but not exactly the definition. But I need to make small quantitative definition. So we want the other eigenvalues to be small. This one is k. We can't play with it, but we want the rest to be small. And I'll show you why. So here is the most. I think if I had to say one thing about pseudorandom graph, that would be the expander mixing lemma, which asks the following question. So here is your graph, and there are, as we said, edges from G to SG, and I take two subsets of vertices, L and M, and I ask how many edges cross between them. So how many edges go from L to M? Now, if everything was random, then we have here, let's say L is of size L and M is of size M. If everything was random, then we have L edges. L LK edges leaving L. Every vertex here has K. This is the K. Has K outgoing edges. So the expectancy is LK, edges going out, and for each of them, what is the probability that I land in M? It's M over N. Right? That's the proportion of element in M among the group. And the expander mixing lemma tell you that this is roughly right. So it says that the deviation of the number of edges from M to L from the expected value, which is K L M over N, is bounded by something which depends on this parameter. So this is the...
Well, again, can you explain
But-
that again on K and N and N?
Yeah, so this is K, N, and these are the sizes. So there's L and M, and there are LK edges going out of L, and each of them has probability M over N to land in M. So that's like a good guess, and it turned out to be correct according to how much the graph is pseudorandom. We said we wanted this to be small, and it also depends on M and L, but only on their square root.
This kind of explains why would you think.
Let's prove. Great question. So let's do the proof. It's very simple. You observe that the number of edges is just the inner product of applying the adjacency matrix to the characteristic function of M. So this will take, we started with L. So this takes the characteristic function of L and then apply the adjacency matrix. So it takes every value here. So it takes this one here and puts it on the endpoint of every edge going out. And then to ask how many of them fell in M, I just need to multiply by the characteristic function of M. So this is where this comes from. And then we do spectral analysis. We say, okay, this can be decomposed as the part in the constant and the orthogonal part. The part in the constant is L over N, constant L over N. That's the projection to the constant. And let's call the rest, let's give it some name. So phi of L is the characteristic function of L minus its projection to the constant, and and we're going to use the fact that it's orthogonal to the constant. And now I'm going to take this thing and decompose it according to this decomposition. So I get A of this part, so L over N1, and here M over N1. And this part is A phi L phi M. Right? Because A acts separately on the constant part and the orthogonal to the constants. So I can see, like, I decomposed this into a sum and this into a sum, and then A acts on each component separately and they're orthogonal to each other.
Can you just explain the notation again? So the characteristic function is just one in the locations that correspond to L?
Say it again?
So can you explain the decomposition again?
How did I get from here to here, or this?
This. Yeah.
This one? I mean, we have, I really think about this space. I decompose it as the constant and the orthogonal space to the constant, which is really the space, the function which sum to 0. And any function I can decompose into the constant part and the orthogonal part. It's really an orthogonal decomposition. And you can do the computation of the orthogonal decomposition of the characteristic function of L to the constant. It has to be a constant function, and you changed it by something of sum 0, so it means that the sum stayed the same. So here it was L, and here it's L again. So this is why this is the projection, and then I call the rest phi of L. And now this A, we know it acts on the constant by K, so this is K L N A1, and this is M N 1, and together this is K L M over N. So this is the part that we expected to get.
The red marker, I don't think people can see.
You can see it?
I can see it, but I think I'm the last person.
If I change it to black?
Yes, black is
Or is it about the place or the color?
No, the color.
The color. So here we got the K L M over N. It's better.
That M should cancel, right? Because it's an
You get N from the 1.
Yeah, there's over N, and the sum cancels one of them. And this is the error. So this is what we call the error. Error. And we're just going to bound this by Cauchy-Schwarz by A phi L phi M. And because phi of L is orthogonal to the constant, it means that this is bounded by lambda S. Phi of L, phi of M, because everything which is orthogonal to the constant gets hit by something bounded by lambda S. So it shrinks, and this is bounded by lambda S of the original function before I took the projection. And this is really lambda S ln. So that's the whole proof.
Can you, before you erase, give some intuition again for what exactly this lambda, what's the role of the lambda? Because somehow from this theorem it seems indeed that it kind of dictates how close is your graph to randomly distributing the nodes. But can you give some intuition? What is this lambda?
Yes.
Because I think maybe I didn't fully understand the decomposition, and then I wasn't sure exactly.
So let me say one thing. Let's look at lambda 2. Maybe this will give some intuition. Lambda 2 is bounded by lambda 1, but I claim that we can say when they are equal. Lambda 2 is equal to k if and only if the graph is not connected. Because the graph is not connected if I can find two functions with eigenvalue k. And if there are two connected components, I can take a constant function on one of them and 0 on the other, and this will still have eigenvalue k. So say, and by the way, because we're in groups, this is the same thing as saying that S generates G. Because then I can go from any element to any element using S.
This is connected.
Yeah, let's do it like that. Lambda 2 is smaller than k if the graph is connected, if S generates G. So being far away, it means that, so I would want to say that lambda 2 is much smaller than k if x is very connected, which would mean that S really generates G, like very effectively. That's kind of one way to think about it.
Ori, this is also equivalent to the fact that the number of four gongs is the right number?
So that depends on the regime. In some, it depends on how sparse, dense is the graph. At some regime, yes, but I'm not sure when. Okay. So this is the expander mixing lemma. And the second thing that...
So far, where have you used the fact that it's a Cayley graph?
That what?
That it's a Cayley graph and not just some graph?
Never. It won't come up at all.
So, is there any reason why you brought up Cayley graphs?
Because I want to talk about unitary groups soon. So I'm already talking about groups. Oh, yeah, but everything holds for graphs in general. And I'll do another one, which is mixing. So let's take a random walk. So random walk on the graph. And it means that at every time, I have a distribution on the vertices. The vertices are the element of the group. And I have a distribution. What is the distribution at time t? At time 0, let's say I started with some starting vertex v naught. So I have the characteristic function of this vertex. And to advance from time t to time t plus 1, I have to apply that adjacency matrix and divide by f. Because that's how probability works. To see what happens at the next step, I need to see where could I have come from and sum these probabilities. And this means that pt is, by induction, a over k to the t, p naught. And again, I'll decompose this to a over k, the projection onto the constant, which is now 1 over n, and the complement, which I'll call again phi of v naught, which is just it's just 1 v naught minus 1 over n 1. But I give it a name, so I don't need to write this every time.
Sorry, AS and A are the same? What is AS?
I write S if I want to remind myself that everything came from the S that I chose, and changing S would change the adjacency operator. Yeah, but I won't write it all the time. A is AS. And okay, so this is really the uniform distribution. 1 over n everywhere, so this is uniform. And when I apply the Markov operator to the uniform distribution, it stays uniform. So this stays 1 over n. And the other part, a over k to the t times phi v naught. Again, because phi of v naught is orthogonal to the constant, it means that this decreases it. So the norm of this is bounded by lambda, which is, I'll write here lambda of s, over k to the t. And I need to add the norm of phi v naught, but it's actually almost 1. So what I really see here is lambda over k to the t, which means that as time progresses, this part decays exponentially fast, and I'm left with the uniform distribution. So the distribution at time t converges to the uniform distribution exponentially fast, but the rate of convergence is exactly lambda s divided by k now. So here's another measure of randomness. So this is what we call, this is what's like 20 minutes on what is a pseudo-random graph. And now I'll try to...
So what's the definition of a pseudo-random graph?
that lambda s is small. That the adjacency, the eigenvalue of the adjacency, except for the first one, are small. Yeah, the smaller they are, the more pseudo-random the graph is.
Oh yeah, sorry, I don't understand the terminology that you're using. Hi, can you hear me? Yeah, so on the Zoom. So you have this property that's just saying that there's a spectral gap, but you call it pseudo-random. I mean, is there a reason? Is this a term that's used in the literature? Do you call it pseudo-random?
I don't understand.
I cannot open the lecture.
Can you hear me?
No, I understand the question, but Yes,
Could you relay the question?
So the question is, why are you calling this pseudorandom? Because I'm just repeating what you asked, Zvika, because there's a problem here in view. So
So I gave
pseudorandom because it's a particular object. It's very different than the definition, for example, that Zvika is using for pseudorandom. And Zvika was asking, is this a commonly used a definition, and where?
in graph theory there are like 10 different definitions for pseudorandom graph, and they're all equivalent to this.
Yeah,
That's
I think it's different than, very different than the notion that we're.
No, it's the same thing. That's what I want to show.
But okay, let's talk about it afterwards.
Yeah. So this is what we call pseudorandom in graphs, and we connected it to the mixing rate, the rate of mixing, which is how fast the random walk converges to uniform distribution. And I connected it to the number of edges between sets. Does it behave according to the like the random model, the expectancy?
Is there an S that would be small enough so you call it random and not pseudorandom?
No, random means that somebody tossed a coin and generated the graph randomly, and then you would have the same properties, and that's easy to show. That's Erdős. That's like 100 years ago or 80. But these things are from the 80s, realizing that using the eigenvalues of the graph, I can get behaviors that look like a random graph, even though my graph is a specific one.
In this sense, for example, it's kind of different from what it's because it's not like pseudorandom is not a special case of or
Of what?
it doesn't become random in some external condition.
Something random.
You could start doing these oracles, like building a program that has to guess if this graph was generated randomly or built using this machinery, and allow some complexity and build this theory of the same thing. We'll say something about it in a moment.
Well, I think he's asking if there's some way to make something to infinity or something so that you get real random.
To get real random?
Or if there is some kind of way to.
If I'm thinking cryptographically pseudorandom, then I say it's secure even against unbounded adversary, then it's random.
Yeah, I'm not familiar with this language.
I want to ask it in a different way. Basically, I think what you're saying is this. Suppose I could randomly pick a pseudorandom graph from a family of pseudorandom graphs. I mean, in pseudorandomness, what you do is you pick a pseudorandom object and you compare it to the distribution over a random object, and you ask whether you can distinguish between the two. And I think the way you're looking at pseudorandom graphs is similarly. You give me a pseudorandom graph from a distribution of pseudorandom graphs, and I need to distinguish between this graph and a completely random graph that was chosen, like what you said, every edge is chosen randomly according to some probability. And I need to distinguish between these two objects, these two distributions. You say it's very hard to distinguish.
Okay.
It's not clear.
Depending on what the model of access. If you only do a random walk on the edges of the graph, you won't distinguish very easily. Depending on I think this is what Ori said. That this is the connection.
I'm saying more that if I want to think about one graph, really. I want to think about one graph and say I'm doing something random, like taking a random walk or taking two random sets in the graph and asking how do they look like.
Just to connect it to Zvika's notion of pseudorandomness, you would need to
I want to do something which might connect it. So I want to connect it to this day. So now let's just replace my finite group with our favorite projective unitary group, so PUD. And now we can talk about what is a pseudorandom object in this group. And I'm going to take again a set.
Can you remind me what's the projective unitary group?
Who asked? Unitary groups modulo scalars, which is the group of gates in quantum computation. But you could take, and everything I say from now on works for any compact group. So that's the only thing.
It's not SUB, it's something else. You don't
It's the same. It's the same as PSU. Same group. Okay. So I'm going to take. You want you? I'm fine with you.
So it's not unitary anymore.
Let's take you. I mean, I really don't care how this thing. You like you? It's the same. Any group, any compact group will work. So I'm taking a set. Let's do it again. Symmetric, and let's call the size k. So it's a finite set, and I'm going to look at the Cayley graph of G with this set. So now this is an infinite group, but I can still ask about the Cayley graph. This is an infinite graph with, here are unitary matrices which are connected to other unitary matrices. And well, it will never be connected, because if I start from a vertex and then I apply an element of S and another, I'll only see countably many vertices, and this is uncountable. So there are infinitely many connected components. But I can look at the adjacency function, adjacency operator again. It's still well defined. I take a function on the group, and because this is finite, I can still sum over the k translates. And I'm going to take the adjacency operator, which came from my set, acting not on the set of all functions, but let's start with all continuous function. Because there is a topology here, and I need to take it into account somehow. So if I look at continuous function, what happens? So again, AS of the constant function is k. And I can ask, is k also in the spectrum after I take this out? So let's say if the spectrum.
So you're not taking the whole group, but continuous functions on the group?
Only continuous functions on the group. I take the whole group, but only continuous functions. And I ask, is the multiplicity of k in the spectrum 1? And there it was saying that S generated the group. And I want to say that it's the same thing. So if S generates the group, but now this is topologically. So it means that I take all the products of elements of S, and then I take the closure. I take also the limit points. And if this gives me all of G, I really claim that this is if and only if the multiplicity of K is 1. What you call universal. That S is universal. I can approach any element arbitrarily using S. Let me convince you. So if
Can you say what is the topology of this?
on the matrices, the real topology of real, it sits inside MDC, the complex numbers. So if, let's do it one way, if S is a proper subgroup, if what generated topologically by S is a proper subgroup, then I can take its characteristic function, and that's fine. I'll get k times, because when I apply A, I stay in this set, and this is not 1, so this is not everything. So I get another eigenfunction. Should I show the other way around? I'm not sure I have time to get to everything, or leave it as an exercise. What? It's okay to leave it as an exercise. And it's very similar to what you do in the graphs, in finite graph. No, I want to say it because I want to say where this is where the continuity comes in. So the idea is if I have a function which satisfies this, then I find a point where fg is maximal.
Well, if it's not continuous, that function is not continuous.
That's a good point, but yeah, make it continuous. In a second, I'll stop thinking about continuous. So I'll take a point where fg is maximal. Let's say it's positive and has maximal eigenvalue, and then look at the neighbors, the k neighbors. I know that summing these neighbors is going to get me k times what I had here before, and because this is maximal, it means they have to be all equivalent to it. So these also have to have same value, otherwise I can't get k times what I had before. So it means that if I take a point and I look at its neighbors, I get the same value, and their neighbors, and their neighbors, and their neighbors. So it means that eventually f, if I take g, and then I take everything generated by s, this is an infinite set, I think, probably, but it's constant. On this set by this combinatorial argument. And now, because of continuity, I get that f is continuous also on the closure. But if this is g, now we assume that s generates g topologically, this means that f is constant. So the only function with eigenvalue k is a constant now. So this is how the topology brings us back to what we know. And really, you don't want to think about continuous functions because, as Alon showed, I even don't know how to do that. You really want to work with the Hilbert space. So this is the Hilbert space of square integrable functions up to changes of measure 0. This is where spectral theory works. And this is the space we'll stick with from now on. And now we can write the spectrum of the adjacency operator on this space. And it's again lambda 1, which is k, and then lambda 2. But now it's an infinite. And yeah, there are infinitely many eigenvalues. And I'm going to do the same thing. I'm going to write lambda s to be maximum lambda I, where I is at least 2. Maybe this is bad because I can't really order them now. So let's say different than 1. And it doesn't have to be a next one. There can be infinitely many before it. And this is what I want to say, that if lambda s is small, then s is a pseudo random generating set. So we already saw that if lambda 2 is also k, then it's not even generating. So I want everything else to be far away to say that it's even random. So what can I do with it? Okay, I'll stop now and say the idea now is that I have a topological generating set for the unitary group. So I fix one set of generators. Here's my favorite one. This is the best one, in my opinion. The best generating set for U2. This is probably even SU2. I'm going to write PU2 because that I'm sure of, but maybe it's even in SU. You need to compute the determinant to check. That I can write it easily, and it's really explicit, and it has the, and lambda S is really minimal for this guy. Yeah. Maybe I'll say something about this. So I'm just giving it now as an example. And for this one, I can compute lambda S. It's 2 times root of 2, which is smaller than 3. K is 3. It's 1, 2, 3. These are 2 matrices. What?
It's smaller than 3, but by a small margin.
By the maximal possible. This is a Lambopana.
What?
This is Ramanujan.
Okay, but still it's small.
And this is what we call golden gates?
Yeah, that's what we call golden gates. Maybe I'll say. Of what? What is it? I didn't try to do that. Like, what angle is it? I can do it later.
Yeah.
But this comes from arithmetic root, right?
Yeah, this comes.
You're going to show
But it's going to be something rational.
Where it came from?
Yeah.
No, that takes a semester.
No.
No, just give you an example. I want to make it concrete. I'm claiming that this is a very concrete set of matrices, and if you take products of these matrices, of these 3 matrices, of more and more of these matrices, what you're going to see behaves randomly.
So we should use them as our gates for the pattern.
Yeah, that's what I'm like. That's what my grant says. So there are. I want to show. I mean, why do we say that they behave pseudo-randomly?
Can you construct them to be like the best on a single spin?
There are many. This is the simplest one that I could find.
This is for one.
1 qubit.
That's for 2 qubits.
Ah,
And if you have 1 and 2, somehow you can.
If what?
We have 2 qubits.
2 qubit. I'll get you something good.
Yeah.
3 qubit. Whoa.
No,
2 qubit, we have similar stuff. Yeah, so it's kind of, we're very interested in the low regime, which for Dorit, for example, is completely meaningless, I think, not interesting. But I can say it already now that the big challenge here is scaling what we know how to do for 1 qubit, 2 qubit, 3 qubit to general.
But usually we don't use gates with many qubits. In practical.
I don't know. Okay, that's true. But the point is, this gives me a way to be spread fast over U2. Now you're going to say that I can use a lot of copies of U2 to spread fast over UD, but that will be, it won't be optimal anymore. You lose a lot. Okay, so I have 15 minutes, so I'll skip. I wanted to do a continuous version. What?
Don't skip anything.
Not to skip? Dorit, how much time do I have?
Don't skip.
No, I wanted to show the continuous version of the expander mixing lemma, but I think it's less interesting than the other thing I wanted to show. So, can I put this online? Like, if somebody is interested in a continuous expander mixing lemma, but I'll do the other thing, which is the random walk. So, I did want to show an example where we could have
But you wanted to say why they behave pseudorandomly. This is what you want to do?
Yeah, that's what I want to show. But I want to make one point. I could have K not in the spectrum of the adjacency operator restricted away from the constant, but lambda S is K. Because I was sloppy here, and this is not max, this is really soup. This is an infinite set, and it might be all smaller than K, but accumulating to K. And
that would be continuous spectrum, that's what
no, it won't be continuous. It will have, it could be. I'll give you an example. So really the simplest thing is just take U1, which is just a circle, the complex unit circle, and take e to plus minus I square root 2 pi, and any irrational number would work here. And then you can compute that the spectrum of the adjacency operator is exactly 2 cosine n, that would be n square root 2 pi, as n goes over the natural number. That's a very easy exercise, just that's Fourier on the line, on the circle. And then if I'm taking away the constant functions, then I'm taking away 0 here. And after I took away 0, you won't get 2 here ever again, because you only get 2, and this is a whole multiple of 2 pi, which it won't be. Again.
The spectrum is usually a closed set, it's defined as a closed set.
In that sense, yes. And the spectrum is the closure of this thing, so yeah, I could put this. Yeah, but before I did the closure, I don't have 2 in the point spectrum. But still...
You won't have it in higher dimensions.
In what?
Would you have it in UV?
Good question. Is every...
Because here you basically want to generate something to be amenable.
So you ask whether being an expander is a property of the group or of the generators?
I'm saying that you won't have such an accumulation with these, like for dimension greater than 2.
No, I guess not. Property T, right? We have stuff.
The generated thing would have to be amenable.
Yeah, yes. Yeah. But this is a case.
This is what Alex said in the first.
Yeah, that's what I tried to. So what happened here is that lambda S is 2, which is K, but because it's the supremum, because we get 2 as the supremum of all of these values, which means that these are topological generators, but not pseudorandom ones. That's what I want to say. So this is a generate, but not pseudo-random. Well,
accumulation of the spectrum would imply that the discrete generated group is amenable, and then it would have to be like virtually solved. There's some group theory.
No, I mean, I'm just...
It's just that you have accumulation. You don't have
No, I mean, by my definition, lambda S should be smaller than 2, then I call it pseudorandom. Here it's 2. But it's 2 because of the supremum. It doesn't appear as an eigenvalue, so it is a topologically generating set. This is the distinction. Okay, so I hope I can...
But I think that some of the Kitab actually shows that, like what Alon said, that above, for not for U1, but for U2 and above, everything is going. This is not
to be every certain. Not according to my definition, actually.
No,
I don't know. Not every generating set has a spectral gap, right? Otherwise, why do you need?
Every generating set would, because it's exponentially approaching, you won't have.
Maybe just not.
I mean, we have Bourgain-Gambourg, we have huge work showing that certain generating set have spectral gaps. So we definitely don't know that every generating set has a spectral gap.
Yeah, I don't think they need spectral gap for Solovay.
Yeah, that's
No,
true.
they don't, I know, but they thought that.
If you want, if you had the spectral gap, then you'll get Solovay-Kitaev with C equal 1. Always.
So you'll have a gap which is 1 over, you have a non-constant gap.
I mean, you could have no gap, you have lambda s equal k, but still Solovay-Kitaev works. What? Yeah, maybe now. Yeah, I'm going to look at random walk. So I would want to look again at A over K, that's the Markov operator, and apply it many times to one starting point. So I'm starting at some element and applying the random walk operator. But the point is, in L2, this is 0. This is a function which is 0 everywhere and 1 on one element, and L2 is only defined up to measure 0. So if you're a physicist, you would put here a Dirac something, but I'm not a physicist, I'm not allowed. I can get my license revoked if I do that. I need to replace it by something with a measure. So I'm going to approximate. I'm going to take the characteristic function of a ball, some epsilon ball around my starting point. And I'm going to start from this neighborhood of the starting point randomly. And now everything works fine. So this is, let's do the same game. This is A, K, T. And now I want to decompose this into the constant part. The constant part, you know what? I think if I want this to be really a distribution, I need to divide here by 1 over epsilon. This is uniform distribution on this ball. Right? Because I need the integral, yeah, I need the integral to be 1. Yeah, so that's the normalization. So, so this is my P0. That's the distribution at time 0. It's the density at time 0. And then I decompose it into the constant part, which is exactly 1. And the complement, which is 1 over epsilon, 1 of the epsilon ball, minus 1. And as before, we'll call this phi. And as before, this part stays fixed all the time. This is the uniform distribution on all the group, and I apply the Markov operator, the random walk operator, it stays uniform. And this part gets shrunk by, so this is A over K to the T phi. And this part is bounded by lambda S K T. Times the norm of phi. Now we do need to compute the norm of phi. And it's roughly epsilon, right? I did it at home. No, 1 over epsilon. This is roughly 1 over epsilon. And you'll see why it makes sense if I'll have enough time.
Can you maybe explain what is this ball you're considering and why are you considering?
Why what?
Why are you considering this ball? Like,
where
do you see it in the previous?
Okay, I want to do the following. I want to start at a point on the unitary group and then apply these S, and I start a random walk on the group. And I want to use spectral theory to understand what I get. But spectral theory doesn't see isolated points. For them, I can change them to 0. I have to take something with a mass to apply spectral theory. Once I take something with a mass around my point, now I can apply spectral theory. Yeah, and it will connect to the fact that eventually what I want to say, I can't ask, can I get to this element? Because we know there are uncountably many elements and my walk only see countably many. I really don't get everywhere, but I want to ask whether I get to the epsilon neighborhood of an element. Do I approximate elements? Which makes sense.
And basically this is a random, you're basically doing a random walk on the random circuit, meaning you have your generator,
yeah.
And you're now talking about some distribution over one surface.
So, like in Sheila's talk, she was talking about the same something like that, but if it also need to be taught as well, or something that has is not like something that is not seen by the kids.
Connecting here now.
So here's the question. For fix epsilon and ask for which L as a function of this epsilon is every element of your group, epsilon close to S to the L, which means taking a product of L times element from S. L-wise product of element from S. This is the basic question of circuit length.
Epsilon net.
Epsilon net, yeah. And so what metric? And for us, the reasonable metric is the following. Say G is in, let's say G is epsilon close to G prime if G is in a ball of R volume epsilon around G prime. And this makes sense because now I understand what can I do if I want to cover all of G by balls, and each ball has volume epsilon, then absolute bound, it's easy to see that I need to have at least 1 over epsilon, many points. Every point gives me a volume epsilon around it. To get, maybe I didn't say that, we always assume that the total volume of the group is 1. That's our normalization. So to get to a volume of 1 from balls of volume epsilon, I need 1 over epsilon. And if I take, this is at most S, this is at most K to the L. So I understand that I need at least L has to be at least log K 1 over epsilon. This is an absolute bound. And now I can say what random does. So you keep asking about random. So this is like in Zvika's talk. Now I generate real random Haar independent uniform random matrices, and we can show that. Okay, let's fix the question. Almost. Sorry. Before I answer, I need to say we're going to ask about almost every G. We're going to miss some sparse areas which are very hard to get to. This is kind of like asking about average case rather than worst case. So in random, to get almost everywhere, what you need, you get almost covering, almost.
What is the measure you are using?
Covering.
So what? The measure you're missing is
the measure?
Yeah.
That's the measure. I'm saying that.
No, the measure you're missing, the almost.
I'm going to, I wanted to go to 0 as epsilon goes to 0. That's my game. So it's almost epsilon covering if and only if L of epsilon is log k1 over epsilon plus little omega of 1, which means anything that goes to infinity, and go to infinity sounds big, but this already goes to infinity. Go to infinity as epsilon goes to 0. But this already goes to infinity, and here I can go much, much slower. So I can take this to be log, 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 log 1 over epsilon, it will still work, and this is if and only if. This is kind of balls in beans, coupon collector. These are the classical exercises in probability, in generating a net. And this is what we're competing with. So this is the absolute bound. This is the random. And we want to get as close as possible to this. And what I hope to show you is that we get L epsilon yeah.
What's the exact statement? What does it mean, random?
What?
What's the exact statement? What does it mean, random?
It means that you generate k to the L here. You generate k to the L random matrices in U2 or in any compact group.
Okay, you pick it how random?
How random independently.
You pick that number.
Yeah. I picked that number because I want to compare it to my S to the L.
You get it covering, which is like, that's why you have coupon collector, etc.
Yeah, it's very, very close to the, is as close as I want to the absolute bound. And what we get by spectral methods is k over lambda s square 1 over epsilon plus omega 1. What? So if I wanted to prove this, so that's if I don't have time to prove it, I'll just say what are the consequences.
What's written the log to the base?
K is the number of generators, size of S. Lambda S is this.
Yeah, so this K over lambda S squared is in the base of the log?
It was? That's the base of the log, yeah.
That's the base of the log.
Yeah, that's the base of the log.
But it's funny because if lambda S was K, you regain the
If lambda S is K, then this is log 1 of million and it's infinity.
Sorry, yes.
Yeah. So that's why I need this lambda K to be smaller for this to make sense. But the interesting part is, what do I need to make it optimal? What do I need to get to the volume bound?
Lambda S always has a lower
Square root of K. 5 דקות. Okay. So lambda S equals square root of K gives.
But doesn't the 2 kill you?
Random.
Or it's
Right.
not backtracking?
What?
Doesn't the 2 kills you, or it's directed analog or something?
We can talk about it. It's interesting. So square root of K, right? We started with K generators. If the rest of the spectrum is bounded by square root of K, I'm as good as random. That's my point. Now, I wanted to prove this by this. It really comes from here. I don't think I have time to do that, but I'll put it online. It's like one board taking the random walk, starting from an epsilon ball, looking at what happened after t steps, and getting from here to here is like just moving agapim. How do you say agapim? Huh? Sides? Yeah, moving sides, sync around. So I'll say this you get from the random walk analysis. So really starting from an epsilon ball and doing the analysis, you'll see that this is how fast you get almost everywhere. What?
This you can also put on the web?
Yeah. It's like 4 lines. So how much time do I have?
4 minutes.
4 minutes. So I'll say now I'll say a bit about what can we do. So around 86, I think, Lubotsky, Phillips, and Sarnak started looking at this question and showed two things. So for any S in U2, I have to do PU2.
They call it distributing points on spheres, right?
Yeah, the paper is called distributing points on spheres, something like that. So for any set of k elements in PU2, lambda s is at least 2 times square root of k minus 1. So this is really too optimistic. You can't get to square root of k. You can get possibly up to 2 times square root of k minus 1. That's the lesser part of the paper. The other thing that they did is that for any prime p, which is congruent to 1 mod 4, they gave s with k being p plus 1 with this value, lambda s equal. And this value, for people who came from graph theory, they know this value well, and this is what's called the Ramanujan. Ramanujan graph, Ramanujan bound, Ramanujan spectrum. And then from this you get that if you want to epsilon cover, so you get epsilon cover of almost all of G at L, which is roughly 4 times log K 1 over epsilon, and probably right? Something like that. Because of the 2 here. And then we had a lot of work improving this. So the idea, as Gil said, of noticing that because our set is symmetric, we have a lot of redundancy. If I take an element and then it's inverse, then I'm getting back to a circuit which I already have. So we can do better analysis when we count only reduced words. So words with no cancellation. So in a paper with Peter Sarnak from like 7 years ago, 8 years ago, we managed to show that for these generators you can go all the way to log k 1 over epsilon, but you need to pay an extra something like 3 log 1 over epsilon, which come from stuff that people who do analysis, non-backtracking walk analysis know. And when Dorit talked with me about what she wanted me to show today, I told her, like, okay, the conference is in 2 weeks. I'm not going to prove anything new by then, but I did, which is made me very happy. So last week, I managed to remove this and get all the way to random. So
this the no-go statement of Lubotsky and Sarnak.
This thing?
Yeah, because you just noticed that there is
there is a lower bound, which is this 2 square root of k minus
on the spectral gap. But the analysis that I do to get this from the spectral gap to the covering is really like 3 lines spectral analysis of the random walk, and you can be cleverer and do more sophisticated stuff, and we've been doing that. And I think really last week I kind of closed this chapter because we get all the way to random. So this is as good as random. So we can say now that LPS in U2 is as good as random. But now, yeah, this is U2. So how do you take things further? It's a big problem. And I will say the most interesting problem, I think, in this field is the fact that all of this is not explicit. We know that at this time, we know that there is a word in S of length L, which is epsilon close to your element, but we don't know who it is.
So that is constructed, but this is not.
It is?
Yeah, it is. There's another word. Yes,
Okay, so making these things effective is like the most interesting part. Thank you.